couple of these exercises. Now, you might have seen that exercise 1 is mostly part that we had done during the actual lecture. If you have to recall what the exercise was, feel free to take a moment. But there was this idea that if you just believe the Einstein equations, the ones that tell you how your metric will look like or how your line element will look like, that one will tell you that your expression for the line element should be something like this in a spherical symmetric situation. Right? I mean, it should be Minkowski, but with a small deviation of the form k over r, with k a constant. So this mathematical form comes directly from the Einstein field equations that we haven't really touched upon yet. But let's just take that as a given, and then the question is, do you understand why the k must be at least contain a mass, the mass of the thing that curves the space-time? So no equations, just do you understand why that is?
There has to be mass to curve space-time.
That's all there is to it, really. Yeah.
I saw the question, but I wasn't sure if it's...
yeah, sometimes the quizzes are too simple, maybe, or what?
No, yeah. No. You're just a genius. Maybe, yeah,
No, in all seriousness, I mean, at the very least, you expect there to be gravity, or in our current language, a curved space-time, simply because there is mass around. You already know this from Newton, so at the very least, it should be a mass. So k must be some function of mass, otherwise you have nothing to curve space-time. And then by exercise B, you have to tell why then it's a linear function of mass, so k is not m squared or m to the third or the logarithm of m or something like that. It's directly proportional to m, and that's really the question. Any ideas? I take it there's no ideas.
Is it not because if mass doubles, then curved space
should also double, something like that?
Because there's
It's basically the same question, right? Like, why should it double is then the question.
Yes, I mean, you're taking now as an assumption that the curvature will also double with more space time.
If there's no logo, like, I don't know.
No, it's a good attempt. Some other ideas, maybe? It says by dimensional analysis, so there's a hint there.
Sure. So something with the units of the g and g squared. So because the total constant of stuff in the brackets should be dimensionless, right?
Why is that?
Unitless.
Dimension of a radius, so of a distance.
No, because it's just a factor multiplied by, for example, dt squared and multiplied by dr squared.
Well, it is of course true that if you add things together in physics, they should all have the same unit.
Yeah.
And if you look at the line element, each and every single term of that has the dimension of a length. Right? It's the left-hand side is a velocity times a time, well squared. So that should give you length squared. So left side and right side of the whole line element should have the unit of length squared. Now the last two terms of right-hand side are length squared because it's r squared times a dimensionless unit, angles. So that's Panos, I think. Yes. Oh, hi.
Hallo.
Heb je deze nodig?
Ja, die kunnen we goed gebruiken. Ja.
Sorry dat ik iets later ben.
Maakt niet uit.
Het was gewoon
We hadden besloten heel erg hard te schreeuwen. Dat we dan ook wel
super. Dankjewel voor het
Ja, graag gedaan. It's not the right cable.
Oh boy. Nice.
Okay. Otherwise, just keep on recording. She's ready to go. It's some cable. Yes, it's black, but really that's the only, and it has two ends. That's really the only.
Well, one of the two ends is a USB cable as well.
Yeah, you're right, but this has this very special one.
Yeah.
So anyway, let's just put it here for
Good show.
For good show. So people at home think that we're using a microphone and we're being professional. So.
Well, on the recording it already says you can hear that.
Damn it. Yeah, you're right. Edit this out.
Yes.
Okay. Yeah. So all of it should have all parts of this equation should have the unit of a length squared. So you can just tell by my dimensional analysis, but that tells you something about what the unit of k should be, or can only be. In fact, it already shows because k over r itself is being subtracted from a dimensionless unit. So
K has to have the unit of R.
yes, k has to have the
Of
unit
length,
of r, of
basically.
length.
Yeah.
Yes, meters.
Isn't that what I just said?
Yes, it is.
Yeah.
Yes. So Louis is not the only genius here. You're
Oh,
also-
no. Okay.
No, but you're right. It should.
Mm,
All geniuses here.
yes.
Okay. Does it help us?
It should. So we have a. What are the units of G?
Well, let's figure out what the units of G are.
Something Newton per kilogram per second.
Well, you
So
can-
it comes from the gravitational force Newton's. So G and M over R squared. So it's
Over Newton times kilogram
Yeah, let's
over seconds.
put
Yeah.
everything into units. So this thing is a Newton. This one is still G. Typically, people put these square brackets
Yeah.
around it to say
Yeah.
the unit of and such. This is kilogram squared. And this is meter squared. So G, the unit, is then Newton meter squared kilogram squared. And we can do better because Newton itself is
Mass times meter squared over meter over second squared.
yes, meter over second squared because Newton itself is mass times acceleration. So the
Yeah.
unit is kilogram per meter per second squared. So if you put everything together, then you know that G in total, I always forget what it is. I have to rederive it every time that I use it. It's meter to the third over second squared kilogram. By the way, do you expect a G to be there in your line element? Or in your K, if you will?
what's
G not defined by mass itself.
Is
Small
G-
g, the small g.
oh no, big G.
And big g.
No, small G, 9.81 meter per
yeah.
second squared. Yes, that is defined by the mass. But this big G, the universal constant, the one that always applies when you have gravity.
Wait, what was the question?
Would you expect big G to be in the line element? Or your deviations from Minkowski? Slightly related question. In what kind of physics does the G pop up?
Oh, I'd say no, actually. You wouldn't expect it in the line element, right?
You would or you would not?
You would not.
You would not, okay.
Because your line elements, just the plain one, is in a case that there is no gravity there,
Yes.
right? And the G would only pop up in physics where gravity is present.
Yes. But we have a curved space-time, and curved space-time is gravity, yes?
Yeah.
I would say that it needs to be there because it's a constant that kind of quantifies the force that you will get in the end, so it should be somehow included in the Christoffels.
Yes. Yeah, we're all saying pretty much the same thing. I mean, whenever you have gravity, universal gravity, you expect G's to be there somewhere, capital G's. And you can even say it should be in the K because it's the K that differentiates this line element from a Minkowski line element where there is no gravity. So if there is gravity, you expect a big G, and therefore you expect it within the K. So it should be. So we now can conclude that whatever K is, it should contain a mass and it should contain a capital G. Oh, and it should have the unit of a length. So we now have a sort of a mathematical puzzle. How can you, by connecting G's and M's, both of which we know should be there in there somewhere, how by connecting these things together can you make something that has a unit of a length?
So, 3.
Okay, you can't really do it just G and M, right? Because then you still have your seconds that you can get rid of.
Okay, that gives us another piece of information.
That is we've lost.
Just by G's and M's, every time that you introduce a G, you will get back seconds.
So you'd need something. So if you, sorry, so you need a velocity at least to
Yes.
get rid of this, because you need to get rid of
Seconds.
seconds, but also of m squared,
Yes.
right? So you need to divide by m squared and times by seconds squared.
Yes.
So if you have a velocity, if you square that, then you get rid of those.
Yes. That is
But
very
we
true.
have c squared in the equation. Is that velocity we're talking about, or
That is the velocity that we're talking about. Yes.
Yeah.
So just to be sure, from the dimension analysis, you can tell that there should be a velocity squared in there. But why, of all velocities, do you expect that to be the speed of light? And the answer is not just, well, it's because of relativity. That's too easy. There's a very good reason, but it's one that you might even piece together. But it's deep. It's conceptual understanding. So at this point we understand there should be a G in there because gravity. There should be an M in there because curvature. And to get the units right, there should be c squared in there, or it should be a velocity squared in there. Why is that velocity the speed of light?
Does it have something to do with the space-like and time-like nature of the separation or something like that? Because if we say that it is at the limit of time-like and space-like, so maybe that's like the boundary condition at which gravity starts to act.
Yeah, I'm not seeing that exactly because if I would put in, I mean, I understand the argument, but if I would put in a different velocity than c, say the speed of sound, your condition says that at some point space-like should go into some the time-like. I think this is sort of your argument, what I'm hearing.
Yeah,
Does it also happen in Minkowski space-time? Yes.
I'm not really sure. I was thinking about like one specific case, but I think it doesn't make sure in general. Doesn't make sense in general.
Well, my counter argument would be, well, you can always make the k go away again, but just taking a small amount of mass, and you would not even notice the c squared in the first place. So what I'm saying is, if we're going to pinpoint this velocity by looking, oh, but I know that in Minkowski space-time such and such should happen. Well, if you go to Minkowski space-time, that's another way of saying that you should put m to 0. But if you put m to 0, then the whole k over r thing will be 0, regardless of what velocity you had put in. So apparently that's not a discriminating factor. Now there's a deeper meaning. What do you know about velocities if you go from one observer frame to another observer frame? Take the Lorentz transform, say.
Maybe it's because it's the only velocity that is invariant for all the observers.
Yes.
And that is your line element.
Yes. Because the line element has to be invariant.
Yeah.
Remember that? The whole line element. Now, if you're going to put in something that is not invariant, you're breaking that rule.
Yeah.
So, okay, there we go. Now, now we're there. I mean, from physics we know that the thing should k should be proportional, or there should be a mass in there. We also know that it's a gravitational thing, so Newton's constant should be in there. But then you see that if you try to combine g's and m's, you end up velocity squared short, and the only velocity that you can use, because you have to keep the invariance of the line element, is c squared. And then you find that there is really only one combination that does it. And that is k is, well, the one that is given, gm over c squared. Waiting for somebody maybe to make a comment here.
It's not a,
Sorry?
it's not the mass missing.
No.
It's the numerical factor of 2 in front.
There's the numerical factor. You cannot find the numerical factor by this dimensional analysis, right? If you put the number 17 in front, our arguments would still hold. But apparently this is not what nature shows. And this is why I made a comment here. You can pinpoint the numerical constant, that it is 2 and not 17, by taking this line element, looking at the situation where gravity is very weak, so there's gravity but very weak gravity, and then you expect things to look like Newtonian gravity. And the only so you could write down the geodesic equations for this line element, and make gravity very weak, and you should get back that the acceleration is equal to that thing. And if you do that, you will find that there's a factor of 2 missing. That's the factor you have to put there. So it's by comparison with Newtonian gravity that you know that of all the numbers you could have put in front is 17. So that's where the 2 comes from. And finally, we now have this. K is that number with maybe some number in front. K of r even. And then there should be an r here. There you go. But do you agree that this has no unit, this is no unit, so this you can subtract from that one, from Minkowski one, but well, to the power of 17 would also work, right?
Yes.
So you might wonder, why not take the power to the 17? It's not a question, but it's just maybe some trivia that you might find interesting. Maybe you can think why there's no power 17, or power 2, or square root, why it is to the power 1. It's not for dimensional reasons, because I'm showing you now that the dimensions are okay whatever power you take.
I think intuitively I would say because nature tries to minimize the energy in the system. Or like
Have we ever talked about energy in this context?
Not minimize the energy, but minimize the action.
Yes.
So I guess that if you could take it to the 17th exponent and take it to the first exponent, it would be more minimized if you don't take it to the 17th exponent, right?
No, that would actually help if you took something to the 17th, because you're subtracting it from your proper time. You want to minimize the proper time.
Oh, okay.
Anyway, just food for thought. This thing, if you plug in the numbers, we talked about this before, this is, I forget what the number is, it's 10 to the power minus 11 divided by c squared, which is about 10 to the power 17, including the square. 11 17 is power 10 to the power minus 28. This is a very small number for a given m and r. So in principle, you can say, well, you take that small number, take it to the power 17th, and it becomes ridiculously small. So you could say that Schwarzschild maybe is only the first order approximation of a deeper law. It's just that the deeper law is so ridiculously behind the decimal point that we might not be aware of it. And that is still an open possibility in relativity. It's just that 10 to the power minus 28 itself to some power is vanishingly small. I mean, this thing itself is already small. So there is a school of thought in relativity that says, well, maybe Einstein's general relativity is really just a first order approximation in an even bigger scheme of gravity.
But what are we looking for? Like, what would be the effect of if it would be like if there would be other orders? What would be the effects or?
Yeah. Well, first of all, they will be
What
very
would
small.
the use of it?
Yeah, I understand. Well, for one thing, everything that we've done, including the conclusion that things will move in such a way the proper time is minimized, that will still hold, even with the extra powers. But that would just mean that your line element will now contain all these extra powers with it. Your Christoffel symbols will, so your geodesic equations will. It just means that you have extra little mini forces on top of your gravitational force. And that would reveal themselves in how things would move through space-time. But again, this is ridiculously small.
But just more detail, like just more details.
Yes, more detail in the motion. But again, so small that is cannot probably measure it. But there is a school of thought that works on this.
It applies to smaller particles, maybe.
Oh.
Then everything should be affected by gravity in the same way.
Oh, that is a good comment, because what we were.
I once for relativity I wrote like a paper of the particles themselves obey equivalence principle. But they were not really sure. Like depends on how you see the data interpreted.
Okay, so there's is that because there is some error on the data that is difficult to read, or?
I don't remember, but there was like conclusion. There was like no real conclusion. Like depends on how you see it, but they are testing on it.
Well, this of course also has to do with it's hard to drop small particles.
Yeah.
To do the measurements on these things.
Yeah,
but it's true. I mean, they do equivalence principle tests on big things like black holes and how far. One of them, and you might have heard about this, is the lunar ranging experiment. That they've actually put a mirror on the surface of the moon. On Earth, they shine a laser to this mirror. It reflects back, and by the laser light, they can just calculate how far the moon is at any moment in time from the Earth. And as both of them are traveling around the sun, of course you have to subtract that they also travel around each other, but as both of them are traveling around the sun, the equivalence principle, the weaker version of it, says that both of them should have the same motion due to the sun alone. Again, you have to subtract their motion around each other. And by this lunar ranging experiment, you can actually tell if the moon is pushed a little bit differently than the sun is, than the Earth is due to the sun. And those results, I forget what the numbers are, but it's 10 to the power minus 13 difference or something like that. So as far as they can tell, there's no difference. But these are big objects for which you do these things. So anyway, so that's exercise B. I would not be surprised if this is one of the ways that Schwarzschild himself might have found a solution. Well, it must be something like this-ish. And then fiddled with the rest and then found a working solution.
Basically just trying things out then.
Yes, but it's an estimated guess, as in it must look something like this-ish. Okay. All right, C. Show that dr is the radial distance between two events as seen by an observer who is stationary infinitely far away. This relates to the point that we made on Monday, that if you are given a line element, or a metric if you will, that you first, one of the things that you have to do is identify whose time and or whose distance it is that is mentioned in that line element. If you find an r, who is the guy who measures that r, if any? Right? Because lengths are different from one observer to the next, and we've now seen this not just because of the relative motion, but also because of their position in space-time. So if you find an r, you have no idea whose r it is. I should say dr. Whose dr it is. Or same with dt. Now the dt we have identified. The dt that you have in this line element is the amount of time between two events as seen by a guy infinitely far away who himself is not moving. Now the claim is the same with dr. dr is the amount of radial distance measured by a person who's infinitely far away and who is not moving. But the question is, how can you tell? That's exercise C. I'm really asking you, can you do the identification step?
So we tried, but we got to some answer that seemed wrong.
Okay.
Yes.
Maybe we can try the first steps, if I can find it somewhere in my notebook.
Okay. Would you like to do it on the board maybe, so we can all see?
Do you have it somewhere?
On the
At
board.
least do you remember how we did it? Because I have it here, but I tried to recall how we actually did it.
There was one thing we were wondering when we were doing this for the derivation of who measures dt, so to say. We assumed that dr was 0, I think.
Yes.
Do we do the opposite in this case? If we try to see who measures dr, we assume that dt is 0, or do we not?
That's a good question. Why would you do that?
Well, we did it just for symmetry's sake, basically.
Yeah, that's what I'm thinking. When you want to identify what dt is, you put dr to 0, and maybe then the opposite also holds. If you want to know what dr is, you put dt to 0. The answer is, by the way, is yes, but
Wait, don't you put dr to infinity?
no,
No, not dr.
Dt. No,
There's a confusion between what an r and a dr is, I think. Yes, okay. Anyone? Blanks?
So starting with dt equals 0 would not be the way to go then?
Yes, it would.
It would.
Yes.
Okay.
It's just that the argument is not by symmetry.
Oh,
You just do the opposite thing as before.
okay.
No, it has to do with the physics. And maybe if you think back to when we derived the Lorentz contraction in special relativity, there was a condition in order for you to measure a length of something.
Yeah, for like length contraction and time dilation to work. For one of them, the events had to be in the same location.
Yes.
There could be a difference in time. In the other, there could be a difference in time, but they had to be in the same location.
Yes, exactly.
So if we have dt is 0, then we have dr, I guess.
Then the whole.
If you want to measure something's length, you better make sure that you measure its front end and its back end at the same moment in time, yes?
Yeah.
Otherwise it might be moving away in the meantime.
Yeah.
So what you do, you take your two events, right? You always think in terms of events. The two events are measuring the front end of a thing and the back end of the thing, now in radial direction. And you have to do these at the same time. Otherwise something might have moved into the black hole or a little bit away from it or something like that. So to be sure that whatever you measure is a length in the first place, you have to make sure that you do the two events at the same time. So that puts dt to 0.
Right?
What about d tau then?
Well,
We've already established that dt is d tau, right?
only for the observer who is infinitely far away.
True, yeah.
Yes.
But that
Yeah.
is the case here, right? That's what we're trying to prove.
Well, what we have here is now that if we put dt to 0, don't you see, we end up with the d tau squared being minus, right? Because the only positive thing in the whole line element we've now removed. All the other things carry minus signs.
Yeah.
You will see that?
Yeah.
So that we come to a mathematical difficulty, because if we want now to calculate what d tau is, you have to take the square root of a negative number, so you get something imaginary.
So you say that this could only hold when d tau is 0 as well.
Not necessarily, no. No.
Okay, so that's
Mm-hmm.
Do you remember it was something like this? That you have d tau squared minus ds squared, just by definition.
Yes.
Okay, so we can get rid of that pesky minus sign by just redefining our d tau as an
That's
additional minus.
cheating.
No, it's not cheating. No, there is a reason.
Yeah.
Yeah.
Okay.
I know it sounds like cheating.
It
We have a
looks-
minus sign we don't like, so we're going to.
Yeah.
Yeah, I know it sounds like cheating, but it isn't. There's physics behind this. Now, suppose that we do this. Then in our situation, what we have is ds squared is, what else do we have left now? 1 minus k over r to the power minus 1 dr squared. By the way, I'm going to set the phi in the theta to 0 as well. There's no physics there. That's really just the exercise. I'm asking for the radial distance.
Okay.
So something is aligned towards the black hole. That's just the exercise. So I have this. No minus signs, by the way. So I can now safely take the square root of both sides. There you go.
So you set d theta and d phi to 0 as well?
Yes.
Why?
Because we're looking at something radial. The exercise says, show me the radial distance, something that is in the line towards the black hole. So there's no theta or phi difference between the front end and the back end of the thing.
So I think now what we're going to want to do is see for what r dr is equals to ds.
Yes.
And the only one for which that actually does work is when the k of r term goes to 0, which is what happens when r goes to infinity.
ds equals dr at the moment that you are infinitely far away.
Yes.
So apparently ds, and here's where it's not cheating anymore. I mean, this is actual physics. You find that ds itself defined in this way is the length of something as long as you look at it from infinitely far away.
So in this case, it's because what the ds is.
What we did here,
You take
we took it to infinitely far away. We're that observer again, the guy who's infinitely far away, whose r is infinite.
I don't really understand why we are doing this. Like, because we could just assume from the beginning on, okay, this far away, then we just put r to infinity, and then
Well,
gives us
the problem then is if you just do that from the start with the whole expression for c squared d tau squared, the d theta squared and d phi squared are all both multiplied by r, so you're going to get some terms racing
yeah,
up
but
to
you said
infinity.
it's 0.
That is true.
No, okay, but there's some mathematical little snack there because exactly what we're doing now. We're multiplying in infinite squared times a d
But the tau
times
is
0.
0.
Yeah, but you have 0 times infinity. That's always
Always a struggle.
always a struggle.
Oh,
So,
yeah.
let's ignore that for a second. I mean, the struggle is real, but let's ignore it. Yeah. So what we have here is that apparently you can see dr as the amount of distance, radial distance, as long as you are infinitely far away. But I did make a step and said, well, I defined this new thing. Don't worry too much about that. This is something that you also do in special relativity. Because in special relativity, let's go there again. We had this minus dx squared, dy squared, dz squared. There too, if we decided to measure the length of something, and for the same reason, you have to measure the front end and the back end at the same time. So the two events are the two measurements, front end, back end. That means that this one is 0. We had the same issue there. But you know that this is the length because it's just Pythagoras' theorem with a minus sign, right? Mm-hmm. So just from looking at this and recognizing from Minkowski spacetime that this is really just minus the length of something, you can immediately tell that you are allowed to define ds, including the stupid minus sign and the c squared, as a thing. So it sounded like cheating. Oh, I have a minus sign, I don't want it, so I'm just going to redefine something in such a way. No. I know from my Minkowski spacetime that it is correct. That I have to do this in order to get lengths back, not just in units, in actual physics. Look, it's just Pythagoras' theorem.
But the minus is still there in that case. Like, how do you?
Where is it still?
It's still minus ds squared.
Yeah, that's true.
How do we get rid like
Because now if we set these two together, you have a minus sign that drops out everywhere. Here, there's an important lesson here. What I've been telling you so far, up in the last 4 weeks or so, is that when you have the line element, I erase all my line elements. If you have a line element, then I told you d tau, it's d tau squared equals this whole series of things. And I always told you d tau is the amount of time as seen by a guy who sees two events happening at the same place. What I'm now telling you, if somebody asks you, but I want to know not the time between two things, but the distance between two things, what I'm telling you is, replace d tau by ds in this way, set dt to 0, and then the line element in this new form will also give you the length. So the line element is not just a measure of how much time passes between two events, it's also a measure how much length there is between the two events.
If you use ds squared instead of d tau squared.
Exactly. The only thing you have to do is switch your d tau to minus ds with the c squared somewhere, and you can play the same game all over again. So we have the line element tells you more than just the amount of time between things. It also tells you the length.
Interesting.
Yeah, what's very nice about this is, if we make this analogy again that I've used before, that if you have a triangle and the principle of invariance tells you that this number should be the same, and this is the amount of time, and this is the amount of space, right? You've seen this before. And I told you, in order to keep this number the same, if you make the x's smaller, then the t's should compensate in order to let this remain the same value. But that means also that you can reduce your meters and get seconds back. You can also increase the amount of seconds, and so that means you make this one taller, and then this one has to compensate by becoming smaller. So you can go from meters to seconds back and forth in relativity. And that's really what I'm doing here. I had a line element in this way that gives you something about seconds, but by redefining it in such a way, it gives you something about meters. They go into each other. Now, why the minus sign? Because it sounds strange. Well, that is that same minus sign that was there all the time. There was always this extra minus sign somewhere that nobody knows where it comes from. That's that minus sign again. So next time somebody asks you what is the distance between two events, take the line element, replace d tau squared by ds squared, and then just calculate from there.
Is the existence of that minus sign something that people have just come to accept, or are people still trying to figure out why it is there?
I don't know if people do active research on where the minus sign comes from.
How would you do that?
Well, there is a way. A friend of mine who worked this out once, and then I took it to my general or my special relativity lectures in a different setting. I might actually do it next year when I'm going to do special relativity. What you can do is start with a situation where you're not assuming the minus signs or the plus signs, but you just say there is a space-time, which has certain symmetry properties. As in, it should look the same if you go to the left or to the right. Whatever effects there are, it should work here. It should also work in that direction, right? That there's no directionality to whatever laws of physics there are. And also homogeneity. That means that whatever works here should also work here. And if, sorry, yes.
Sorry, if there is no directionality, does that also imply that there is no causality in that system?
No. There's still causality. You can prove that that is the case. Now, if you start with that as our starting point, so that's a one layer more abstract than we've been doing, namely a line element with some minus signs. If you go from symmetry arguments, you will find that there's actually 3 types of distributing the minus signs over the line element. One of them is all of them plus. That just gives you back Newtonian physics. One of them gives you the minuses. Again, that's Newtonian physics. And there's a last version, just from mathematics alone, tells you there's also a possibility that the space and the time have a minus sign difference. And from that moment on, so what I'm saying is that you have this minus sign difference between space and time comes from underlying symmetry principles. But there's only one of 3 options. And at that point, which of the options is the one that nature chose? That distinction has to be made by experiment. So there is a deeper meaning here. We just took it as a starting point. But you see the minus sign goes far here, right? I mean,
yeah, it does, yeah.
But more like why nature chose that. That's like possible to actually find it.
Well, not really, actually. If you take the minus sign,
Yes.
so you're not taking all of them with plus signs, what you then have is, well, actually, there's another option. I'm sorry, I'm just getting sidetracked. I'm sidetracking myself. Three options. One of them is they all have the same sign. Okay? And then I said it's Newtonian physics. That's not really true. I was just not being correct there, factually incorrect. One option is that the time one comes with, detaches itself from dx, dy, dz. So whatever you do to space will not influence time. That's the Newtonian one. Because in Newtonian physics, however you move, wherever you are in space, time will just flow with the same amount.
Yeah.
Then there's an option where all of them have the same sign. That's one that I worked out at some point. You get some very strange world where the rules, there are rules, but they're just different than ours, and the experiment tells us that's not the rules that follow. And then there's the opposite sign version. Yeah, what can I say? I mean, we know from experiment that ultimately, if you take that minus sign into account, you get one of the rules you get back is that the speed of light is the same to all observers. And in a certain way, that even without experiment, that sort of makes sense. Not that it's the speed of light per se, but at the moment that you find that there is no reference velocity from which you can calculate all other ones, that there's no velocity that is the same for all, then that means that you have introduced an absolute rest frame. That there is a frame in which all velocities, or where a velocity goes to zero. And that's philosophically not pleasing. I mean, that's not a real argument philosophically pleasing, but well, in the realm of philosophy now, I guess. To me, there is. If I were to make a universe, and I would have to choose between a universe where there's this one frame, and from this frame you have to calculate everything, or I make a universe where all frames are equally valid, which is equivalent to saying there is a light that is a velocity that has to be the same for all, then to me it sounds more aesthetic to say that there's no preference in nature for what observer frame you choose.
Sounds a bit communist.
That we should all be alike or something like that. Yeah, well, I guess.
Everyone would be cool.
Well, because now it leads to a deeper question. Suppose that we take all the plus signs options, and what I'm trying to tell you now is that this is equivalent to saying that there is one absolute observer frame in which physics works and the rest doesn't work very well. Then you can ask the next question, why would it be, right, you have 15 million frames and only one frame works, why would it be that frame and not the one next to it? You get to a deeper question, why is there a choice made? And to me, it's just philosophically pleasing that there is no choice made at all of them work. Anyway, yeah. We just take the minus sign as a given.
Bottom line.
That's the bottom line, yes. Anyway, okay. Well, we also really have exercise D now, because what we now have is, this is the amount of distance measured by a person. This is the amount of distance measured by a guy infinitely far away. If you want to calculate, some guy infinitely far away says, I see 2 meters between two events. And somebody within the space-time says, I see a different amount. The guy within space-time measures this. The guy infinitely far away measures this. And they can just relate these two things to each other. Just like you do with time. Right? In the time case, what we have is, if you know dt, it's the amount of time that is measured by a person infinitely far away, you can calculate how much time somebody else has measured by some factor like this. We wrote it down a couple of days ago. Gravitational time dilation. We now have gravitational Lorentz contraction. If somebody tells you how much distance there is infinitely far away, that's this number, then you can calculate how far, what the distance is for some other guy by plugging this factor in front of these two people. So if you will, this is gravitational Lorentz contraction, but I struggle to call it Lorentz contraction because it doesn't contract, it expands. So don't use that term anywhere outside of this classroom. Gravitational
Expansion.
yeah, but that depends on the space-time. It might also be time, space difference then, or something like that. Distance
Space
difference.
change,
I'm not sure if there's
space
enough.
variation.
Variation, distance variation, something like this. We made up our own word here, and you can just tell what the number is, and that is actually exercise D. Suppose that a person infinitely far away sees that there is dr difference between the two things. This guy, does it measure a bigger or smaller amount? The guy who's actually there. Let me draw the situation here. Here's the black hole. Here's a guy infinitely far away. Here's a length in radial direction, because everything is radial in this exercise. And there's a guy here looking at this length, and there's this guy looking at that length. Who measures the biggest length? This guy says, I measure the R. This guy says, no, I measure the S. Which measures the biggest number?
I would say DS if R can be bigger than K.
If R is bigger than K. Yes, R is bigger than K.
I would say DS.
Is the S a smaller number?
Bigger.
DS
Bigger.
is bigger, right?
And there's a 1 over in there somewhere.
Yeah, that's why
okay,
bigger.
okay, good. So the S then would be 1 minus K R square root the R. So for the infinite guy, this is just this. For the non-infinite guy, this is some smaller number, so let's get mixed up about these things. So you have 1, you're subtracting some number, the number that you subtract is not 0, but it's a bigger number, so this becomes smaller, so this whole thing becomes bigger, so ds is a bigger number than dr. Okay, well, that's what happens when you get close to a black hole. You get pulled apart.
Nice.
Is that the spaghetti?
Yes, that's officially, that is an actual term, spaghettification. You can find that in actual articles on black holes.
That's a really
You look up the concept of spaghettification and compare your result, because you're literally being pulled apart. And a couple of days ago I told you that black holes are dangerous for a couple of things. One of them is you get sucked in, you don't come out. The second now is you get stretched out.
But will you notice that, or will you feel that, or to you in your reference frame that is approaching
No.
the black hole?
You actually feel that. You actually feel that, yes.
Well, you feel it for like this much time, and then you're dead.
Yes. But the people from
You do feel
outside,
it.
here's a third effect, that people from outside looking towards the black hole see everything happening in slow motion. So that person sees you being pulled apart in slow motion. He sees your agony for eternity or something like that.
Lovely.
Yes.
But-
These are monsters.
So if you
these.
would go in with your feet first,
Yes.
aren't your feet then in a different inertial, actually a
Local
different-
inertial.
local
Yes.
inertial than your head.
Yes.
So it's gonna, your feet are gonna be pulled apart with a different rate.
Yes, but that's this effect. You're just describing the effect in a different way.
Yeah.
What I'm saying here is the difference, the length difference between your feet and your head is now not your usual 180 or something like that. It's become a bigger number by that factor. The closer you are to the black hole, the worse it gets. So that sucks.
Literally.
Sorry? Literally, yes. Okay. So that happens. I forget what the second part was. If you're then you said, well, but your feet are in a local Lorentz frame, so that your feet don't notice anything. That's true. And your head is also in his local Lorentz frame. It doesn't notice anything, but there is a difference between the two frames. The difference being pulled apart. So maybe your toes compared to each other are not being pulled apart, but because those are in the same local Lorentz frame, but your head and your feet are not. By the way, the same effect is happening right here. I mean, my feet are somewhat closer to the center of gravity than my head is. It's just that the difference is so small that for all practical purposes, my feet and my head are in the same local Lorentz frame. So this is another way of putting spaghettification. The local Lorentz frames close to a black hole have to be ridiculously small in order to be a local Lorentz frame. Smaller than the length of you yourself. And this is why you get spaghettified. Okay. Any questions so far? This is just playing around with the line element. We haven't done any mathematics yet. So I'm greatly looking forward to exercise 2. So I propose we continue with exercise 2. There's 2 more in exercise 1, but that's just, again, playing a little around with the line element. But I propose we move on to 2, so we can do some actual algebraic calculations. You're starting to get used to this. There's a c square wrong. And there's a minus sign wrong.
Yes, we found both, I think.
Both of them, right? But those are the only ones, I think.
Yeah.
Yes.
Just a question, like for E,
Yes.
like now we have the same question, just someone is moving.
Yes.
So in that case, we just say, for example, some angle is not 0, and then we do the calculation.
It depends on how he's moving.
Yeah, but that's what we define then. We
Let's
define
see.
for that question.
No, it's still radial distance, so that means it's somebody moving inward or outward.
Ah, okay.
What would you do then, by the way? You can already tell. I mean, I wanted to skip that exercise, but you can already tell. Suppose, I mean, this is the relation for radial people, yes?
Yeah.
Okay, yes. Now R, you take the location of the guy doing at the position where he measures the S.
Okay.
That's this R. But what if the guy is moving inward? So R is not a constant. What do you do? So? Yes, this R is always the one of the measurer. Yes. But if the measurer is falling inward, he's spaghettified and at the same time moving himself inward, you cannot take this as a constant. So what do you do? This is exercise E. Just really quickly.
Can you put it as dr?
No. But we do have a dr.
Okay.
That's an infinite amount of distance. And it's an infinite amount of distance.
Do we have to integrate time also? Like change over time? That R changes over time?
You could do that, sure. But there's no time in there. So you would have to introduce time. But in principle, you could do it. You can say, well, you know, we're going to divide both sides by d tau or something like that, and then integrate maybe something like that. We can do faster than that. I mean, what we have here is a relationship when the distances are really small. And you can go from small distances to big distances, indeed, by integrating, just adding a lot of small distances. So what you could do is just say, you know what? If I want the actual amount, not just from my one part of my ankle to the next part of my ankle, a small dr, I want the whole of my length, well, I just add all the smaller parts, right? I just integrate. That's what it is. I haven't emphasized this enough, I think, but the line element tells you the infinite amount of distances, the small distances. The bigger ones you get by integrating. And in fact, you can do this integration, can't you? I mean, there's an R, there's a dr. If you want, you can replace it by x's. You can just write down the antiderivative. And because it's a complicated thing, I wrote it down in this manuscript on Relativity where I wrote it down. But it's a logarithm of a square root or something like that. It's not yes, it's a crappy thing, but you can just calculate what it is, and then you have the actual difference. So this will be exercise. Okay. Cool. All right. How's the energy levels? Is everybody okay still? Want to try some Christoffel symbols? I should apologize for constantly getting my C's wrong. Now, let's certainly not do all of them. So any preference? These are really the only ones, the only 6.
We can do the first one.
Okay.
Because then we can show that actually the C was one.
Yes, right. I think there should be C. Let's see what I
so most of the C's that are in front of.
Yes.
They were power of 2 too high.
Let's see what I have.
I have
I have mine here. RTT. t. Here it is. I get this. There's a c squared.
Yes, that should be there, but in the Excel sheet it will only be c to the 4.
Okay. And this minus sign should not be there, and this c
That's-
squared should be missing too. And aside from,
Well, this
We
minus
had
was
two
too much.
others. Those two as well.
again, let's. All right. So. You know why we do this, right? If you have a line element, or if you will a metric, you calculate Christopher's. If you know the Christopher's, you can write down the geodesic equations. From that, you calculate how things move. So I listed the 6 Christopher's, and I propose we do 1 or 2 of them or so, just to see that you remember how this works. Are you volunteering to do this?
Oh yeah,
Yeah.
sure. Oh, with me or Nelson?
Uh,
Because you were looking at me, so.
no,
we didn't
it's
together.
you as.
Oh, we're now just one.
Yeah.
It's like a couple.
You were one entity.
Yes. Okay.
You've lost all your
Haven't heard that
individuality
before,
in this course.
No. Oh, Francesca's volunteering.
I'm good.
Okay.
Shall we do the next year's one?
What?
Do the nastiest one.
Oh yeah. Sure. Start with the first one. But who was going to go to
Let's see it.
Got it?
And
Yes, I do.
yeah, do we have to modify
Maybe.
or do we have to change it?
That one's quite
Impossible.
Yes. Here are the correct ones, so you can.
Yes.
So I'm going to correct them later on the sheet and put on the lay-in. The ones with the boxes around are the correct ones, including the
Can
seats.
I just erase this?
Yeah.
Shall I leave the palm tree there?
It's not mine. Somebody put the palm
When
tree
you
there.
try to pitch someone a business idea, you have to really sharp amount of time. So if you want to start a startup,
Well, we had to do this like 7 hours ago. Like, wait, no, like what gets us up in the morning?
Literally.
My fingers are too slippery.
You need to eat more of these two.
shall I open them for you? It's wrong.
Try popping it.
You need something.
I'll try this like.
Yeah, like it's.
I was ripping it.
One scissors, guy.
Yeah, that works.
We'll be
See, I'm a
shaming
theoretical
you.
physicist, so I don't think of it.
Okay, that's a nice save there. Okay.
What did you
So
say?
if anyone wants carrot, then go for it.
Actually, can I have?
Yes, you can.
Thank you.
Okay, so we're doing
Alright.
Thank you very much.
gamma TTR is the one we're going to do, right?
Anyone?
I'll take one afterwards.
Carrot
Thanks,
bread.
So you're going to do this one, right?
Oh, no.
Yes. Okay, so the one. Shall I first actually write down the formula for Christopher's again? Maybe it's useful to do?
Yes, that would be nice.
Okay. So we're going to have. That's the one.
Yep.
And okay, we can just assume that this one is just the same as the other metric, but then with every element inversed.
Why is it?
Because it's diagonal.
Otherwise, you can
Do you write them down first, maybe? The
Yeah, I can do that as well.
metric, the necessary?
If people want that.
Do people find it necessary to write
Should I
down?
just write the metric down as
Yeah,
well?
would be nice to.
So just do the version with K basically filled in now, right?
Yeah.
By the way, is it not beta instead of mu?
Well,
The, like
you
G.
Because you have alpha beta also.
Ah, no, yeah, okay, no, okay.
G over. As I got to fit it.
Yeah, you're going to You're looking at the diagonal
Go-
matrix,
yeah,
so you could
go the wrong
go
spot.
slide underneath it here.
Yeah, that's true. So this one's going to be the same as that. But then minus 1. This one here is just r squared, and there we have r squared sine squared theta. And then we just say
Yeah, just do that like that. Yes, that works.
sort of. Yeah. So the one we wanted to do was
TTR.
TR, yes.
Can I suggest the following? That you don't specify the alpha beta yet, but you do specify the mu, and then show why the only one that is possible is alpha beta as such. Right, there's,
Sorry?
well, there's two things we can do. One of them is that we
Oh, I see what
say
you mean. Yeah.
mu is TR, I think, right?
Yes.
So you say, well, this is T and this is T and R, and then just calculate what comes out. But maybe a more education exercise
Yeah,
is
actually
to,
nice because this is the only T
yes,
that works, right?
exactly. So my suggestion would be, well, supposing you didn't know that it's the TR one that works.
Let's do
But
that.
so you're going to take mu is T, and then find out which alpha and beta will give you non-zero Christoffels. That is, this is an exercise you will have to do more in practice than checking given Christoffels.
This is going to be all the same. It's the wrong way around. Like this.
Yes, and then the question is, what are the only alphas and betas that make this come out non-zero? Thank you.
No.
Oh, yeah.
And I think there's some more, but it's yours, I think. So would have people have difficulty finding out which alphas and betas will make this come out non-zero? It's an exercise we've done a couple of times. It's much easier if I tell you what alpha and beta are, and then you check that it's true. But let's do the more difficult one. We don't know what alpha and beta are. What are the alpha and beta that make this non-zero? We don't care about non-zero Christoffels.
I was sort of assuming like it's looking at what mu has to be,
Yes,
because I will already specify one of the
exactly.
elements of all of the stuff in brackets.
So new has to be.
Nu has to be T
Has to be
because
It's diagonal matrix.
it's a diagonal matrix. So the other ones are simply zero themselves. So we already know that the contraction over nu will only give you back mu is T.
So fill that in. This. I can say something similar about alpha and beta for this because you here also only want G's that have both the subscripts the same.
Yes.
So alpha and beta could both be T. Or isn't that the right way to say it?
Well, they cannot both be T at the same time.
That's true.
So one of them is T.
Mm-hmm. The other one has to correspond to a coordinate with which you can take the derivative.
Yeah, exactly.
And in the case of T, that would only be R.
Yes. So two lines of two pieces of argumentation here. if you want to have this one to be not zero, then beta has to be t because of diagonal matrix. So beta has to be t. But that means that you're looking at this thing, and you have to take its derivative, but you can only take its derivative with respect to r. So that means that if you're going to take beta as t, then alpha has to be r.
Why only R?
Because the
T, theta, and phi do not appear in the expression of this metric element. So you can't take the derivative with respect to those.
so apparently one non-zero version of this Christoffel symbol is when beta is t and alpha is r. You still have to work out what that thing is, but you can tell it's a non-zero one.
Sorry, could you explain how you're structuring the matrix? It's not really clear. From
I mean, this here.
yeah, and
That's because it is ran out of space. It's not really clear.
so which means
It's actually like if you draw lines between for the columns and such. Basically have let's see. This could be one element.
makes it makes
So
it more
it's a
complicated.
4x4 matrix.
But it looks like the Christoffels are included in the
Yeah, that's
matrix.
just because I drew this too close to that.
Oh,
so this
right.
is not
No,
part
no,
of it.
that's just a notation.
This is
thing.
just diagonal.
That one.
And this is
All
like
right, thank
imagine this to be not there, just like filled with zeros.
You just
instead.
did that to
Yeah, I got
confuse
scared
us,
a bit.
Yeah, so there's a Christoffel symbol
No,
within
no.
the matrix. So
Yeah.
that's like
Luckily
inception
not
in
the
general
case.
relativity,
Luckily
right?
Is that a thing or?
No, because it isn't hard enough, so we have to make it more.
Not yet.
I think if there's a physical reason why it can't be. Well, you just continue. I just,
Yeah.
I just tell you about this.
So just like take the situation where alpha is t, beta is r, for example. Because
it could be the other way around.
it could be the other way around, yeah.
Yes, due to the symmetry.
Yes.
Indeed.
Well, you can already tell here.
We can prove that symmetry thing from here.
Well,
You can, yes.
you can tell. Yeah, you can tell that alpha, reversing alpha and beta is just reversing these two, so you'll get the same Christoffel. So that
Yeah.
means once you have found alpha is r and beta is t, then you also know that alpha is t and beta is r will also give you a right Christoffel symbol. You don't have to calculate; it's going to be the exact same thing.
Lovely.
And one more thing, just to help you along. This one is going to be 0 anyways, right? The last
Because
one.
t derivatives will never give you anything
Exactly.
because there's no t's.
But that means we have.
Isn't it super zero? Because it's also
Uh,
the element that you have.
Oh, that is also
It's
super
a super
zero.
zero.
It's
a
also
super zero.
it's also super zero.
Yeah.
That's true. Yes. Yeah, because that's true. Okay, but that means that you can already tell there's only going to be one Christoffel symbol with T upstairs. All the other ones are not there. So there's only one. Well, two. I mean, there's T
There's a
R
symmetry
R T,
thing,
but
yeah.
it's you can say that one thing.
Yeah.
So but that means there's really only one Christoffel symbol with T upstairs.
Which would be this one. Which is equal to
Yes.
this. And then we can work it out. So just like fill in the elements
Yeah,
right away.
just use T is alpha is T and beta is R.
Let's see. This would be multiplied by 1 minus 2.
Oh, okay, yeah.
This is then the TT upstairs. Right?
That's one.
Okay.
Yeah, to the power minus one.
Yes. And we just take the choice of TR. This will be the one you're going to use. You're going to have R here, so you can take your R derivative, and T there, so we have GT. This multiplied by R, well, multiplied by R derivative. The element here would be same as that one, but then not inversed.
Just get minus.
Yeah.
There's not a minus there.
Minus 2 mg squared. then we actually take the derivative of that metric element. You're basically taking a derivative of two different things. You're taking the derivative of this one and of this one. This one's just constant, this basically drops out. And the derivative of this, if you would include the minus there, would just be 2mg over r squared c squared.
Yes.
Does anybody want me to show that as well, why that's the case?
It's just derivative taking.
Mm-hmm. Okay. Then I'll just write it down. This minus is still there though, so this one survives.
Exactly.
Yes. And then
Well, you're done really.
yeah, you can like rearrange it to resemble the shape on the sheet a bit more.
Yeah, and then you will see that
The
I had a
volume
c
covers
squared
more.
too many, and there was a minus sign that should have been there.
Yeah.
Yeah, so
So like the final result would be c squared times 1 minus c squared, and then there is mg top as well.
That's it.
That's one.
So not only have you shown that this Christoffel symbol is, there's a missing bracket.
Yeah.
Not only have you shown that this Christoffel symbol is indeed correct, in fact yours is correct and I had a minus c squared one, but also you've shown that it's the only Christoffel symbol with t upstairs. Now in this way you can go through all of them and find them. So I propose
It's the only two, really.
Oh yeah, that's true, but people typically say, well there's only one Christoffel because of the symmetry, but okay, sure, these are the only two.
Would there be situations in which this would not be the same, why the symmetry doesn't hold?
No, it's always the case because that follows directly from the definition. If here you replace alpha or you swap alphas and betas, you would get exactly the same regardless of what your space-time was.
Also the case for non-symmetric metrics?
No, there it isn't.
I mean non-diagonal.
Oh, yes.
Sorry.
Yes. It's also the case for non-diagonal matrices, but not for non-symmetric metrics.
Mm-hmm.
But
yeah, because then switching these indices around wouldn't give you the same expression anymore.
Exactly. And in fact, this equation would not hold. The geodesic equation would look more complicated because I had to take into account when I derived it. I sent you the link with the derivation of the geodesic equation. I had to assume at some point that the metric is symmetric, and it is. Metrics are always symmetric.
That's nice.
So we had this Russian professor who put this, cosmology professor Mukhanov, and he talked about these things. He always said yes, symmetric is symmetric, and it sounded like he was just saying the metric is the metric. Yes, we know. I mean, but he meant that the metric is symmetric, and he was right about that. So. Yeah. How are we on time?
It is
20 past. Okay. So we can do two things. We can just steam on for another half an hour or so, or have an half an hour, 10-minute break, and then move on. Yeah, good. So I wrote down the geodesic equations that come. This is exercise 2b. Wrote down the geodesic equation again, so you don't have to solve them. The question is just write them down. And what I really wanted to check was if you understood how you can take this general expression of geodesic equation. You would plug in these Christoffel symbols that I listed over there. If you would then get to the right equations. Most notably, if you do the contraction right, as we saw here, the Christoffel with a t upstairs. There's only one of them. That's this one. So that means the Christoffel here with the t upstairs only works if you multiply it with a t and an r derivative, because that's the only one that's there. I wrote a factor of 2 here.
This can switch over it.
Yes, because both of them work. Right? The Christoffel comes with no factor of t, they just calculated it. But in my GLS equation, I do get a factor of t because it works when alpha is r and the beta is t, but also works the other way around. So the option occurs twice in the contraction. So this is why it appears there twice.
And is it not possible to apply the same trick we did last time? Yeah, to say like to solve it, to say like the angle is constant.
Oh, we're doing it after this one.
Well, that's actually exercise 3.
Okay.
Because we're now going to look at what will happen if you're going to look at a circular orbit. Something is moving in a circular orbit. I mean, this is ridiculously difficult, right? I mean, same point that we've seen many times before. If you want to solve what t looks like as a function of proper time, you need the r solution. The r solution you first have to solve in itself, which requires the t, which we were looking for, but also the theta and the phi's, which themselves depend on the other ones. It's hugely complicated. So we're just going to look at a special case being circular orbit. And question 3a is, what would you plug in if you know that it's a circular orbit?
D phi is 0.
Which one is 0?
D phi?
Why d phi?
Depends on how we
Yeah.
move like this or
Depends how
Yes.
D5
depends
is.
on how we're moving.
I'm not getting the point here, but
We're talking about d-phi's, and I said that it just depends on how we define it.
Yeah.
oh, I see. Or how you defy it.
Ah,
That's true. Let's take the theta want to be fixed. So that means that theta is the angle compared to the z-axis. So the whole motion happens in the xy plane.
We did.
Or no, well, actually, it did not specify that. It just said it was a constant theta. We're going to take 90 degrees, and in fact, it's going to be forced on us by these equations.
Mhm.
All right, but so that means that theta is whatever it is a constant. You might ask yourself, why? I mean, I don't have to. Maybe it's some circular motion, but it happens in 2 angles at the same time, right? And there's a deeper law here that says that you cannot do that. It's the same law that happens in Newtonian physics. But once you have a force that is spherically symmetric, like gravitational forces in Newtonian physics, then all motion will happen in one plane. This is why the planets all revolve in one plane. And the same law applies here. So taking this constant is actually forced upon us. What the constant is, we will see in a second. It's pi over 2, but we'll see. What else? Circular motion.
R is constant.
R is itself a constant. But that cleans up everything immediately, right? Yeah, let's do it immediately.
Yeah.
Let's not write down these whole equations again with James Wilson. Jessica, Philip, you might want to have these because this is also one pretty big exercise. The equations hold for your exercise as well. It's just the application is different. But for our case, circular orbit, that means the RD tau is 0. But that means this whole thing drops out. There's some physics immediately, right? Because it tells you that the dt squared, d tau squared is 0. What does it say about time dilation? Before I continue, immediately I can tell I can already conclude something about time dilation here.
Just a constant. The factor with which t can be multiplied.
Yes. Right? We get the same equation again. The second derivative of t as a function of tau is a constant, so that means that t is ... times tau. That's constant time dilation. Now, I expect a constant time dilation in some sense, because we are in a circular orbit, so that means that gravitational time dilation is a constant, because you're at the same curvature around your orbit. Mm-hmm. But how about the special relativistic time dilation? Is that constant? Right? The total time dilation, that's this thing, is a combination of gravitational and special relativistic. One due to your presence in the curved space-time, your location, I mean, and one due to how fast you are moving. everything together is a constant, it says here. Now the gravitational is of course constant because in your circular orbit you're constantly at the same distance from the black hole. But this thing says, well, your special relativistic time dilation is also a constant. What does it say about your orbital motion? If your gamma, if you will, is always the same number. Exactly. You're moving around the thing with the same speed. So look, we haven't even looked at the velocity part, how fast you're moving, but we can already conclude it must be a constant velocity. We don't have a choice. It's just fun that you can already tell just by doing some very basic mathematics. By the way, if you did not pick up on this just by looking at the equation, it will also reveal itself once we get here by the actual phi differential equation. But it's fun that you can already see it here. And how about this one? What drops out?
The second term, the one with dr dθ.
Yes. Okay.
And then the third one too.
Yes. Is that all? Okay, that's a proof. That's not the
The second one too, because the g squared dθ should also be 0.
Which one? This one?
That can be a constant number.
Yes.
Oh, okay.
Yes. It is the second derivative that is 0. That means that the first derivative is a constant. So this is a constant squared. It's not necessarily 0.
Never mind, I thought the 2 was the order of the derivative.
Yeah, I know.
Sorry,
I know.
misread it.
This is why I try to put brackets around it. This means first derivative and that number or function squared, which is different than second derivative. How about this one?
Yes.
I mean, it's we know that r is a constant, so that means it doesn't change, and its change also doesn't change. It's just a constant.
Yeah, if we set theta to pi over 2, then that becomes
1.
Was it 1?
Yes.
So we can get rid of that side.
Yes. Yes. We will do so in a second. How about this?
First term.
First term, of course, is 0. And this one is also 0. Because, well, the theta and the r, this is super 0 again. If you will. But before we continue with the last one, wait a minute. So we have one thing, and in itself has to be 0 in total. It cannot cancel itself out with something else. This thing itself has to be 0. 3 options.
Either theta is 0 or 1, or pi 2,
Yes.
or d phi.
Exactly. So there's 3 options. I mean, the nature tells us this thing has to be 0 if you want to be in a circular orbit. There's 3 options. Either sine theta is 0, which makes theta 0, or the cosine theta is 0, which makes theta pi over 2, or it should not be moving in phi direction. D phi d
Well,
theta.
that doesn't make sense. That would not be rotating. Because you need to have one angle that changes.
In order for a rotation, yes.
Yes.
I mean, the premise of our situation says this one is not 0.
Yeah, exactly.
So we have 2 options. Theta is 0 or theta is pi over 2.
Sin theta cannot be 0
Yeah,
because of the end.
Yes, exactly. So of the 2 options, nature tells you have to take pi over 2 for theta. Because otherwise you get 1 over just infinity. Then you say, wait, but there's also a d theta, so that's 0. 0 times infinity, that's the crappy one. All right, to get rid of that issue, take theta to be pi over 2. And you're right, that means that this one can cancel out because that has become a 1. So, okay, this one is solved, by the way, isn't it? We have 0 is 0 now, so that works. You don't have to worry about that equation anymore. And then the final one, something that drops out.
The second and third term?
Yes.
Yes.
Yeah.
If the body
The derivative between theta and the r.
exactly. Because both of them are coordinate. I'm not sure why I wrote theta and phi, that's wrong.
Yeah, because otherwise you have the phi is 0.
Yes, no, it's just when I copied my equations, one of them should have been dr, I think. This is stupid.
Yeah, the first one should have been dr dθ and pi dθ.
Okay,
Yeah.
there was
Then you can
an
still
R here.
cancel it.
Yeah,
because
you
dr is
still
also-
Yeah, it would still cancel out, of course,
Yeah.
but good, okay.
No reason to panic.
But then we have again d phi is equal to 0 then. Last equation.
No. No, it does not. No. What we have here now, this all of this is 0. What we have here is that the second derivative of phi with respect to tau is 0.
But then we could answer the same for the our before. It says so the second derivative.
Which one? Here?
Yeah.
What about this?
No, because that's d phi d tau squared.
This one.
Oh no, the other one.
Here.
In the third equation.
Okay. Here.
Yeah, exactly.
This one, yeah.
Yeah.
What about it?
This is not the second
No,
derivative.
that's
Can
the
you tell
second
me?
derivative. It's the first
Oh, okay.
derivative squared.
Oh,
Yes.
Okay.
There is that difference again. There's a difference between the second derivative and the first derivative squared. Those are not the same numbers. The second derivative is 0.
Okay, no, that's possible.
Yes. You said this conclusion again, right? I mean, you concluded before from here, where was it? That it should have a constant angular velocity in order for the time dilation to work out. And then I said, well, if you cannot tell it from this equation, it will reveal itself later on, and here it does. Because here you see, well, the second derivative of phi with respect to tau is 0, so that means the orbital velocity has to be constant. This is not our choosing, by the way. This is what nature does. Nature has decided if you want to move around the black hole, and you let gravity do it, right? You're not allowed to use any rockets. If it's only gravity working on you, then gravity will pull you in a constant velocity orbit. Now, we have these equations now. Let's clean up a little bit. That apparently what we have is a constant time dilation. This is the first equation cleaned up. The second equation tells you that mg r squared c squared. No, that's not true. I'm copying the wrong thing. No, it's correct. 1 minus 2 mg r c squared dt tau equals.
Isn't the c squared there in the fraction?
No, it cancels out because what I had to do was take x0, and x0 is defined as c times t.
Oh, okay.
That came with another c squared.
Ah,
And c is 1 anyway. R, the sine squared theta is 1. There's also 4 songs. Yeah. Okay, now we have this. This is the second equation with everything cleaned up. In fact, it cleans up even more.
Yeah, because you can cancel out.
Yeah. So these are not even there. So there's a very clear relationship between the time dilation and the orbital velocity. Which makes sense, right? The more orbital velocity, the more time dilation, that's what it says here. That's what you would expect. The faster you go, the slower your time will go. Which is what it says here. And well, this one is 0 equals 0. Let's write that down. Which is a correct equation. And then there's the last one, and that tells us that. There you go.
So the 0 equals 0, does that mean that we don't really have a condition?
Yes, the third equation does not give us any more conditions. And that's good news. It means that we start out with 4 coupled equations, and now one of them has decoupled. So what we have here now is that if you have a circular orbit, then nature says that's allowed under the condition that you have a constant orbital velocity. That's equation 4. That you have a constant time dilation. That's equation 1. And that the time dilation orbital velocity should be related by equation 2. And equation 3 doesn't say anything. So nature says you can do this. This is allowed. Now I want to add one more step to this. Let's give this thing a name. Let's call the phi d tau. It's a constant. We've seen that here. So free to give it any name. Constant. You typically call this omega. Question. It's an orbital frequency, but who is the guy who measures this number? Somebody measures how fast things are moving around the black hole. Which of the observers is that? It's identification step again.
Say the one that is infinitely far away.
Okay. So if somebody's moving around the black hole and the guy is infinitely far away, says your orbital velocity is that number. It can be. I mean, guys at infinity are also allowed to measure how fast things are moving. It's just not correct in this case. But the question is, can you tell? Whose orbital velocity is this? No, that's not the right question. The question is not whose orbital velocity is it. It's the orbital velocity of the guy moving around it. But who is measuring that number? That is the question. Is that the guy himself who's doing the orbiting, or is it some other guy?
How can we tell?
Well, it's a velocity, so it's somebody's amount of angle divided by somebody's amount of time. Whose amount of angle and whose amount of time
Where's
is
the
it?
hint?
If it was the guy at infinity, you would have had not d tau but dt, right? Because it's the guy at infinity measures dt. You're not dividing by dt. You're not taking his time. You're taking somebody else's time. D tau, as you recall, is the amount of time as measured by a person. The question is, which person is that? We haven't specified. We haven't said whose orbital velocity is. We haven't said who's doing the measuring. We've said who is moving. That we have specified. We haven't specified yet who's doing the actual measuring. So d tau in principle could be any guy at this point. Right? Remember that from a couple of days ago? D tau, there's multiple d taus in curved space-time. Mm-hmm. And we haven't specified whose d tau it is. So we have freedom to do that now. I propose take the guy who's actually doing the orbiting. Then that means that this number, so I've now specified, I mean, you cannot tell from the mathematics, that's just a choice that you make as a user of these equations. Let's make that choice. That means that this omega is the orbital frequency that the guy who's doing the moving himself measures. That's how fast he thinks he's moving around the black hole. That's that number. Now, having named the orbital frequency as such, it's going to clean up equation 2 now. By the way, note that I've now exhausted equation 4, right? That was the only information that was in there. That was a constant. That I've now used, so equation 4 has no use for me anymore. Equation 2 still has use. Let me clean up a little bit. This one goes out. This one goes away. In fact, this has become omega squared. Question, now that I've specified that I'm moving, that I'm the guy moving in this orbit, that I'm that guy, the guy doing the measuring. What is this R now? There's an R. But we also have the R of the orbit. Those are different R's. This is the R of the measuring guy, this is the R orbit, this is the orbit R. That's now the same. It wasn't before, it's because we made that choice. Yeah. It's very important to realize that these R's, these numbers here, are the numbers of the guy who's doing the measuring. This is the guy who's moving. Those are different R's. We've made the choice to make it the same guy, so this R has now become capital R. Orbit. Orbital radius. And we now have a beautiful relation between the time dilation and the orbital frequency. It's this thing. But there's nothing wrong with it, physically. Mm-hmm. What happens if I take my orbital frequency to be 0? I take a non-moving guy. What does it say about my time dilation?
That should be 0 as well, right? dt of d tau should be 0 as well, because
Yes.
you know that the other terms are not 0.
Yes. So no time dilation. Or no time dilation would mean dt is d tau. That everybody measures at the same time. But it says 0. That's strange. So if the guy is not moving, all of a sudden, the guy at infinity measures 0 time between 2 points, 2 moments of his motion. Well, there's no motion, but between two events. How? It's weird. Time dilation, you expect to have some time, and now you have 0.
So like time is frozen basically.
That's what you would think, right? I mean, there's 0 time between, or what you see is that the guy at infinity looking inward is seeing 0 seconds between any two things that the other guy does. So he sees the other guy doing things infinitely fast, because he does everything with no time in between, as seen by the other guy. Which is strange, because I thought black holes slow down time, and now we have different results. So something strange is going on here. We have forgotten something. It's correct, by the way. The mathematics is correct. It's just there's some other piece of information we have not put in yet. It's a condition that all motion in general relativity should have.
Does it have to do with the metric multiplied by the 4 velocity?
Yes.
Also the normalization of.
Yes. You're saying the same thing in different words. All motion in general and special relativity has to obey this equation. All of it. This comes directly from the line element. So if you take your line element, then you have no choice but to also include this. We have not put this in yet. Again, this is correct. It's just not complete. I promise you that if you work this out, we have a couple of minutes left, so we should be able to do it. Unfortunately, the Panos exercise with the cancelling time relations we cannot do, but let's do this instead. I promise you, if you work this out, you will get another condition on your omega. You get 2 equations for omega. Combine them, you get the one omega that is allowed. And that one will solve all your problems. We can do it very quickly, because what does this get you, left-hand side? It's a double contraction. It's a good thing to memorize. Whenever you calculate motion in general relativity, once you solve the geodesic equations, which we have, you always have to put this in by hand. This always has to be true for any motion in curved space-time, but it's not enforced by the geodesic equation. So once you've solved these, this you still have to do, and we have forgotten to do that. So this is why we're doing it now. Well, let's do the contraction first. It's a diagonal matrix, right, or metric.
Mm-hmm.
So that means alpha and beta always have to be the same thing.
Yep.
So in principle, we would have this is me writing out the contraction and using that's the metric tensors diagonal. Now, a number of these things drop out immediately.
Is the EU theta velocity would drop out because theta never changes?
Exactly. One more.
R as well.
Yes. The proper velocity in r direction is 0. Any velocity in r direction is 0. We're in a circular orbit. That means we only have to worry about these two. U phi. That's this omega, isn't it?
Mm-hmm.
U phi means take the phi thing and take its derivative with respect to tau, which is this. So this is just omega squared. Ut. That's also on the board. We just haven't given it a name. Ut is dt divided by d tau.
That's a constant.
It's a constant. We saw that before. That's here. We have never named a constant, but it is this thing, and we know it's a constant.
Gamma?
I wouldn't call it gamma, because you're in a curved space-time, and I be very careful with gammas, because that's really a special relativistic thing, but yes. But yes, I mean, in special relativity, you would call this a gamma, maybe. Or not maybe, you would call this a gamma.
Probably.
And in GTT, well, what is that thing?
This is the first element of your magic.
Yes. Do you know what it is? You can look and see. GTT, of course, is the TT element of your metric, which is minus this thing, dt d tau squared, plus
Is that omega squared? Shouldn't that be just an omega? Because now it's omega squared squared.
That one is r squared sine squared theta.
Yes, but theta in our case was pi over
Oh, yeah.
2. So this becomes r squared.
Yes,
Look, these just constants. A constant plus another constant equals a constant. We're at the end, so let me just say what you can do next if you feel so inclined. What you have here now is an equation for omega. You can solve this for omega. You can have an expression for omega. Here you also have an expression for omega. That means you can squeeze them together and get this one big expression for omega and get an expression for omega. Maybe we should rephrase what I just said. It was correct, but maybe a better way of putting it is this. How many unknowns are there in this equation? Yeah, which are those?
R and T.
No, aren't T?
Omega.
Omega and this thing.
Yeah.
This constant. We know it's a constant, we don't know what the number is. This is also a constant, but we don't know what the number is. The rest we take as given. You are at this orbit with a black hole of this mass. So we have one equation with two unknowns here. And then mathematics tells you cannot solve that. Well, I mean, there's no one solution to it. But look, we have another equation with the same two unknowns. Again, the omega is the unknown, and the time dilation as the unknown. Two equations, two unknowns, is a solvable system. It's not hard, it's algebraic, there's no differentials anymore. The idea is, take this one, take that one, combine them together. So ultimately, if you do that, you will get, it's a mathematical exercise, but not very hard, you will get an expression for omega. And you get an expression for d phi d tau. And both these expressions will only depend on the mass and the radial orbit. They won't depend on each other anymore. So this is a function of R and M, and this is a function of R and M. And it's what you would expect. Because given a curved space-time, and given that you position yourself at some point, the black hole will get you into a circular orbit if you start with the right push. And what your orbit is should only depend on how massive the black hole is and how close you are to it. Because that is the thing that tells you how strongly gravity is trying to get you in this motion. So it's completely logical that ultimately you get an omega that depends only on the mass and your radius and not on anything else. Same with the time dilation. Now, one beautiful thing that we don't have time to work out, but I might do it on paper and send it to you. If you get these two expressions, you'll get Kepler's third law from Newtonian physics, which tells you that the radius of your orbit to the third power is proportional to the square of your orbital time, how long it takes you to revolve around. And the proportionality in Newtonian physics is gm over 4 pi squared, is the same proportionality constant. It just says that Kepler's laws also hold in general relativity, also hold around black holes, not just around the Earth. But that's just a matter of taking this last algebraic step and working it out. Cool. It is cool. It's nice that some properties of Newtonian physics carry over to black holes too.
Kepler even predates Newtonian physics, doesn't it?
Yes, yes. It was it was by Kepler's laws that Newton knew that his equations were correct.
Okay.
Any questions, maybe? Nope.
I have a question
Yes.
from before, like when you asked who is measuring what, like which reference are we, and I didn't get like the hint, like how that you're like measuring the velocity of the guy moving, like himself is measuring his velocity.
Okay. There's nothing in the mathematics that tells you who is doing the measuring.
Yeah.
You get that to decide for yourself. The only thing that is
you mean decide by yourself? Just say like, okay, I'm measuring his velocity.
No. At this point, if you have down these we never specified who's doing the measuring. What we specified is who is doing the moving. That we have specified.
Yeah.
Okay. Now, how fast orbitally he is moving is this thing divided by that thing, and we know that d tau is different for different people in the space time, isn't it?
Yeah.
So we get to decide who of all these people it is. Now that sounds ambiguous, maybe.
Yeah. If I say okay, let's say that the bookkeeper is measuring the velocity.
Yes. Okay.
And we still have the same
equation. Then this tau would have turned into dt because we know that d tau for the bookkeeper is dt. But something else happens too, because where is the bookkeeper? What distance? Infinity. So these r's would have gone to infinity.
Okay.
So it sounds arbitrary to say, well, it's somebody's d tau. Let's just choose the d tau. And you say, well, how can you just choose the d tau? Because any choice of d tau that you make will also change the rest of the equations as well.
And if I say, okay, it's not the bookkeeper, but someone in between.
Yes. Okay. So somebody at a different r, not this, the original r. What was it? Okay, let's do that. Let's go here because I still have it here. Okay. So let's say it's the guy who's doing the measuring. Is not the same guy who's doing the orbiting. Okay, then all of this would still hold.
Just the R.
But let's look at this one. There was an R here. That's the R of the measuring guy. Then this R would have been replaced by the measuring guy's R. And we replaced it by the orbiting guy R because we said the orbiting guy is the measuring guy.
Okay. Yeah.
So again, you are free to choose whoever is doing the measuring, but you have to then put in the R of that guy. Otherwise, it doesn't work.
Okay. So if I specify that this R means the distance measured by the guy who moves around, then it's okay.
Then I replace the measuring guy's R by the orbiting guy's R, and that's what we did here. We replaced all small R's by the big R's.
Okay. Yeah.
And I know. I mean, it sounds like it's arbitrary. How can you have all these? You just randomly put somebody in. Well, the guy that you put in isn't just here, it also appears in the choices of the R and the rest of the equations. So all of it changes. It would be very strange if you had the exact same equations, and then you have a freedom to choose who's doing the measuring.
That's what first I was like confused. Like just say, okay, I measured this guy's, but then it's like the same equations.
Yes, but that of course cannot be. You cannot have the same equations for different guys if you know that there's time dilation, all these sorts of things happening. But that's because choosing your tau, your guy, also means picking your R and your equations corresponds. What's the word here? Responds to your choice. Okay, So I guess that's it for today. Okay, so next week is the 2 weeks from now is when we have the midterm, right? Okay, so that's also that Monday that we're going to have a sort of do we all understand how things are session, but it means next week is just going to be a regular session. We get to choose right here and now. But, we're going to still do cosmology and gravitational waves. So which one would you prefer? They're independent of each other, so we can do whatever order. I'm happy with
Cosmology is more metric work, right? Or wasn't it?
What kind of thing is the cosmology?
The expansion of the universe itself. So that means that our metric is going to be the metric of the expanding
It's a national
universe.
holiday.
Oh, okay. I thought
Maybe.
it was on.
Yeah, we're going to do both of them
Maybe
anyway.
we can,
so-
okay, maybe let's save the best for last. So we can do the cosmology last.
Okay, then.
Or maybe you say that the gravitational waves are better. I mean, you're probably going to say that because you're.
No, I know.
At least I have time. I have nothing else to work on.
Yeah,
For
that's
the repo.
I'll think about it. We'll see. Okay.
Can surprise us.
Yes.
I have a lot
Well,
of
you know, it's going to be one of the two choices. But